Episode 62, titled Switching versus Routing, Layer 2 versus Layer 3 Decision Patterns, the goal is to treat switching and routing as two different jobs for moving traffic, each with its own strengths and failure modes. The exam likes this topic because many network problems come from using the wrong tool for the outcome you want, such as stretching Layer 2 everywhere when you really need segmentation, or adding routes everywhere when you really need local adjacency. Switching and routing are both about connectivity, but they operate on different types of traffic units and different boundaries, and that distinction drives design decisions. When you decide where Layer 2 ends and Layer 3 begins, you are also deciding where broadcast behavior exists, where policy can be enforced cleanly, and how failures propagate. The exam expects you to recognize these patterns and apply them consistently in scenarios that describe new subnets, VLAN isolation, and control points. If you can answer the question, "What boundary am I trying to create?" you can usually choose the right layer without confusion. This episode provides that boundary thinking so you can reason rather than memorize. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Layer 2 switching moves frames within a broadcast domain, meaning it forwards traffic based on media access control addresses and keeps communication inside a local network segment. A frame is the Layer 2 unit of traffic, and the switch learns which device is reachable on which port by observing source addresses and building a forwarding table. Within a broadcast domain, certain types of traffic are sent to all devices, such as address resolution protocol requests, and this shared behavior is part of what makes Layer 2 feel simple and automatic. Switching is optimized for local connectivity, where devices need to communicate as if they are on the same local network and where the overhead of routing is unnecessary. The exam expects you to understand that switching does not inherently create segmentation, because devices in the same Layer 2 domain can reach each other freely, unless additional controls are introduced. Layer 2 also tends to be where loops and broadcast amplification risks appear, which is why keeping it contained is important. When you say Layer 2, you should think inside a local neighborhood where discovery and broadcast behavior exist. Layer 3 routing moves packets between subnets and zones, meaning it forwards traffic based on Internet protocol addresses and connects distinct networks that have their own addressing and broadcast boundaries. A packet is the Layer 3 unit of traffic, and routing decisions are made by looking at destination prefixes and selecting the next hop toward that destination. Routing creates separation because each subnet is its own broadcast domain, and devices in different subnets do not share Layer 2 broadcast traffic. This separation is not only about reducing noise, it is also about enabling policy and control at boundaries, because routing forces traffic to pass through a decision point. Routing is therefore the mechanism that makes networks scale beyond a single broadcast domain while supporting segmentation between different device groups, applications, or trust zones. The exam often tests this by describing new subnets, inter-VLAN routing needs, and policy enforcement points that require Layer 3 boundaries. When you say Layer 3, you should think between neighborhoods, where traffic must be directed intentionally and where boundaries are explicit. A reliable decision pattern is to use switching for local connectivity and to use routing for segmentation and policy, because that aligns each layer with what it naturally provides. Local connectivity means devices that should communicate freely and frequently, such as hosts in the same functional group, can remain in a small Layer 2 domain. Segmentation and policy means device groups that have different trust levels, different security requirements, or different failure tolerance should be separated into different subnets and connected through routing. Routing makes it easier to apply controls because traffic between segments must cross a gateway where rules can be enforced. The exam expects you to recognize that segmentation is not just a security idea, but also an operational stability idea, because smaller Layer 2 domains reduce broadcast risk and speed up recovery during topology changes. This pattern also supports clarity because subnet boundaries become a documentation tool that reflects intent, such as separating user devices from servers or separating production from development. When you apply switching locally and routing at boundaries, networks become more predictable and easier to manage. The default gateway is the router interface for a subnet, and it is the mechanism a host uses to reach destinations outside its local subnet. Hosts compare the destination address of a packet to their own subnet range, and if the destination is outside, they send the packet to the default gateway. The default gateway then routes the packet toward its destination, whether that is another subnet in the same site or a remote network. This concept matters for the exam because many scenarios involve adding new subnets or troubleshooting reachability issues, and the default gateway is often the critical configuration that makes inter-subnet connectivity work. It also reinforces the idea that routing is a boundary behavior because the gateway is the boundary device that connects the local subnet to other networks. If a default gateway is wrong or missing, hosts can communicate locally but cannot reach outside resources, which is a classic symptom pattern. The exam expects you to know that the gateway is not a random address, but specifically the Layer 3 interface that provides routing services for the subnet. When you understand default gateway as the subnet's exit door, routing decisions and troubleshooting become clearer. Access control lists and security policies commonly apply at Layer 3 because Layer 3 boundaries provide a natural choke point where traffic between subnets can be evaluated and controlled. An access control list is a set of rules that permit or deny traffic based on attributes such as source and destination addresses, protocols, and ports. Because routing occurs between subnets, routers and Layer 3 switches often apply these rules at interfaces or virtual interfaces that represent each subnet or VLAN. This is more scalable than trying to control every host at Layer 2 because it centralizes control at the boundary and allows consistent enforcement. The exam often frames this as where policy should be applied to segment traffic, and Layer 3 interfaces are frequently the correct answer because they align with the segmentation boundary. This does not mean Layer 2 security is irrelevant, but it does mean that Layer 3 is the usual place where inter-segment policy is expressed clearly. When you design with this in mind, you can enforce least privilege between subnets, controlling which services are reachable and from where. Layer 3 policy points also support logging and monitoring because traffic crossing boundaries can be observed and audited centrally. A common scenario is adding a new subnet that requires inter-VLAN routing because adding a subnet implies creating a new Layer 3 boundary. If you create a new VLAN for a new device group, those devices will be in a separate broadcast domain, and they will need a default gateway to reach resources outside their VLAN. Inter-VLAN routing is the function that routes traffic between VLANs, typically performed by a router or a Layer 3 switch using virtual interfaces that serve as gateways for each VLAN. Without inter-VLAN routing, devices in different VLANs remain isolated at Layer 3 even if they share the same physical switch infrastructure. The exam often describes this as new VLAN needs access to services in another VLAN, and the correct reasoning is that routing must be introduced or configured between them. This scenario also highlights where policies are applied, because when you enable inter-VLAN routing, you usually also define access control rules that permit only the required traffic. Routing makes the connectivity possible, and policies make it safe. When you can describe the gateway and inter-VLAN routing requirement, you can answer these scenario questions consistently. Another scenario is keeping devices isolated by not routing between VLANs, which uses Layer 3 boundaries as a deliberate isolation strategy. You can create separate VLANs at Layer 2, but the real isolation between them is enforced when there is no routing path between them, or when routing exists but policies deny traffic. In environments where certain device groups should not communicate, such as guest networks, Internet of Things segments, or sensitive management networks, the simplest isolation is often to prevent routing between those VLANs. This isolation reduces attack surface and limits lateral movement because devices cannot reach each other across segments even if they share physical infrastructure. The exam often tests this by presenting a requirement like, keep these networks separate, and the correct answer is to avoid inter-VLAN routing or to apply strict Layer 3 access control lists. Layer 2 separation alone can be bypassed through misconfiguration, while Layer 3 non-connectivity creates a clearer boundary with fewer accidental bridges. This scenario also reinforces the decision pattern that routing is where segmentation is enforced, because the absence of routing is itself a segmentation mechanism. When you understand that isolation is often a routing decision, you can design safer networks. One pitfall is oversized Layer 2 domains, which can cause storms and slow recovery because broadcast behavior and topology changes scale poorly as the domain grows. In large Layer 2 networks, broadcast traffic increases, address resolution protocol traffic becomes noisy, and misconfigurations or loops can produce broadcast storms that consume bandwidth and device resources. Recovery can be slower because loop prevention mechanisms take time to reconverge, and a change in one area can affect the entire domain. Large Layer 2 domains also make troubleshooting harder because issues like duplicate addresses, miswired ports, and rogue devices can have wide impact. The exam tests this by describing networks that are unstable or slow to recover after changes, and the correct diagnosis often points to Layer 2 being too large. Keeping Layer 2 domains small reduces the blast radius of broadcast and loop issues and makes behavior more predictable. The lesson is that Layer 2 simplicity comes with scaling limits, and pushing it too far increases risk. When you see storms and slow recovery, think about shrinking Layer 2 and pushing boundaries to Layer 3. Another pitfall is routing without summarization, which can bloat routing tables and increase complexity as networks grow. Summarization is the practice of representing multiple contiguous subnets with a single larger route prefix, reducing the number of entries routers must maintain. Without summarization, routers may carry many specific routes, increasing memory use, processing overhead, and the chance of configuration mistakes. Large route tables can also slow convergence and make troubleshooting harder because the routing policy becomes more detailed and less comprehensible. The exam often tests this by describing networks with many subnets and increasing complexity, and the correct improvement includes summarization and structured addressing. Summarization also supports stability because it reduces the number of updates routers must process during changes. This pitfall is a reminder that Layer 3 solves scaling problems compared to Layer 2, but Layer 3 also needs structured design to remain manageable. When you see table bloat and complexity, think about addressing discipline and summarization. Quick wins include defining subnet boundaries clearly and keeping Layer 2 small, because these decisions reduce both security risk and operational instability. Clear subnet boundaries make intent visible, such as separating user access, server tiers, management networks, and guest networks into distinct segments. Keeping Layer 2 small reduces broadcast amplification and loop risks, improving recovery behavior and limiting the impact of misconfigurations. These quick wins also support policy enforcement because boundaries become predictable places to apply access control lists and monitoring. When boundaries are clear, teams can reason about where traffic should and should not flow, and troubleshooting becomes faster because you know what normal looks like. The exam often rewards answers that emphasize boundary definition because it reflects disciplined design rather than ad hoc growth. It also aligns with the general principle of least privilege, because smaller, well-defined segments reduce unnecessary reachability. When you consistently push segmentation to Layer 3, the network becomes both safer and easier to operate. A useful memory anchor is switch inside, route between, control at boundaries, because it captures the core decision pattern in a way that maps to exam questions. Switch inside means Layer 2 switching is for moving frames within a local broadcast domain where devices are meant to be neighbors. Route between means Layer 3 routing connects subnets and zones, creating the boundaries that limit broadcast and enable scale. Control at boundaries means policies like access control lists are commonly applied where routing occurs, because that is where traffic crosses from one trust zone to another. This anchor helps you quickly interpret scenarios by asking whether the problem is inside a segment or between segments. It also helps you avoid overusing Layer 2 for problems that are really about segmentation or policy. When you can apply the anchor, you can choose whether a change should be made at Layer 2 or Layer 3 with consistent reasoning. It also makes it easier to explain your answer, which is often what the exam expects. To apply the pattern, imagine being given a problem and asked whether it calls for a Layer 2 or Layer 3 change, and focus on whether the issue is local adjacency or boundary control. If devices within the same VLAN cannot communicate, the problem is likely in Layer 2 switching, such as port configuration, VLAN membership, or local forwarding. If devices in different subnets cannot communicate, or if they communicate when they should not, the problem is likely at Layer 3 routing or policy boundaries, such as missing routes, incorrect default gateway configuration, or access control list behavior. If the requirement is to add a new subnet, you are making a Layer 3 change because you are creating a new broadcast boundary and a new default gateway. If the requirement is to keep devices isolated, you are also making a Layer 3 decision by preventing routing or by enforcing strict policy at the gateway. The exam expects you to choose the layer that matches the requirement rather than to treat the network as one undifferentiated fabric. When you can explain the boundary and the gateway implications, you can answer these questions reliably. To close episode 62, titled Switching versus Routing, Layer 2 versus Layer 3 Decision Patterns, the essential distinction is that Layer 2 switching moves frames within a broadcast domain, while Layer 3 routing moves packets between subnets and zones. Switching is best for local connectivity, where devices are meant to share a neighborhood, and routing is best for segmentation and policy, where boundaries must be enforced. The default gateway is the router interface that allows a subnet to reach other networks. And Layer 3 interfaces are common control points for access control lists and security policy. Adding a new subnet typically requires inter-VLAN routing and a gateway, while keeping devices isolated often means not routing between VLANs or applying strict Layer 3 controls. Oversized Layer 2 domains create storm risk and slow recovery, while unsummarized routing creates table bloat and complexity that can be mitigated through structured addressing. Quick wins come from defining subnet boundaries clearly and keeping Layer 2 small so the network is stable and policies are enforceable. Your rehearsal assignment is a gateway design narration where you describe one subnet's default gateway placement, what it should route to, and what policy should apply at that boundary, because that narration is the clearest proof that you understand Layer 2 and Layer 3 decision patterns the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.